In this second video, we'll continue to discuss the dolphin communication study described in the first video on statistical inference. We need to test the null hypothesis that the dolphins were purely guessing which button to push against the alternative that the dolphins were doing more than purely guessing and were perhaps communicating with one another. In particular, we need to determine how likely it is that the dolphins would have gotten 15 out of 16 attempts correct, as they did, if they were purely guessing. We do that by simulating a situation where they're purely guessing. We can use a coin flip to do this simulation, letting heads represent the dolphins pressing the right button and tails represent pressing the wrong button. Here's some R code for simulating 16 flips of a fair coin, corresponding to the dolphin's 16 attempts to press the button. We see that the first simulated coin flip comes up tails, corresponding to the dolphins getting it wrong. The second flip also comes up tails. The third flip comes up heads, and you can see how the 16 flips play out. Total out of the 16 coin flips, we obtained 7 heads, which is considerably less than the 15 times that the dolphins truly pressed the right button. Of course, we can't draw conclusions from just one simulation of 16 coin flips. We need to do this many, many times and see how often we get a result of 15 or more heads corresponding to the 15 or more times that the dolphins got the right button, which they did. Here's some R code for simulating 10,000 sets of 16 coin flips. For right now, you don't need to focus on the code itself, but let's take a look at the results we get. The histogram shows the number of heads obtained in the 16 coin flips for each of the 10,000 simulations. We see that most often we get about 8 heads. Sometimes we get 7 or 6 or 9 or 10, but 15 is pretty rare. It's way out in the tail. In fact, out of the 10,000 simulations, we got 15 or more heads only 3 times. This suggests that it's pretty unlikely the dolphins would have gotten 15 or more of the signals correct in 16 flips if they were purely guessing. Based on our simulation, we would say that the probability of getting 15 or more correct out of 16 if the dolphins are purely guessing is about 3 out of 10,000, or 0.0003. Because this probability is very low, we have strong evidence that the dolphins are not just guessing and may indeed be communicating. Looking back at our histogram, we see that our result, indicated by the red line over here, is way out of whack with where we would expect it to be, where the bulk of the observations in the histogram are if the dolphins are purely guessing. We've simulated a situation where our null hypothesis is true, where the dolphins are purely guessing, and notice that our observed result is way out of line with the results we would expect to get under that null hypothesis. Therefore, we'll conclude that it's very unlikely the dolphins were guessing, and they may indeed be communicating. This simulated probability that we've looked at has an important name in statistics. This is called a p-value. The p-value tells us the probability of obtaining a result as extreme or more extreme than we did when the null hypothesis is true. In our situation, the p-value represents the probability of the dolphins getting 15 or more of the 16 attempts correct if they really only have a 50% chance of getting any one attempt correct because they're purely guessing. Since our p-value is so small, we have evidence against the hypothesis that they're purely guessing. Small p-values provide evidence against the null hypothesis. You might ask, well, how small does it need to be? And this is really context dependent. Often people use 0.05 as a cutoff point. If the p-value is less than 0.05, people will often reject the null hypothesis. But that's just a rough guideline. 0.1 or 0.01 are also reasonable criteria. When making these decisions, researchers should consider the cost of wrongly rejecting the null hypothesis against the cost of wrongly failing to reject the null hypothesis. In our dolphin study, since the p-value was very small, as we said, it's unlikely we would have observed 15 or more heads if the dolphins were randomly guessing, or I guess we should say it's unlikely that the dolphins would have gotten 15 or more correct if they were merely guessing. So we reject the null hypothesis. There's strong evidence that the dolphins were not just guessing. Let's consider a hypothetical. What if the dolphins had only pressed the right button on 10 out of the 16 attempts instead of 15 out of the 16? Would this change our conclusion? If we go back to our simulation, we see that 10 is not nearly as far out of line with the results we would have expected to get under the hypothesis that the dolphins were purely guessing. In fact, out of our 10,000 simulations, we get 10 or more heads in the 16 flips in 2,299 of them. That's a simulated p-value of 2,299 out of 10,000, or about 23%. 0.23 is much higher than the cutoff points of 0.05 or even 0.1. And it tells us, just by looking at the histogram, 10 out of 16 is not out of line with what we would have expected to see if the dolphins were guessing. So in this situation, it's plausible that the dolphins would have gotten 10 or more correct by randomly guessing. So we don't have evidence to say that they were actually communicating or that they weren't just guessing. We can't reject our null hypothesis in this situation. It's important to note the difference between saying that we don't reject the null hypothesis compared to saying that we accept the null hypothesis or that we somehow have proven the null hypothesis, which are things that you should never say after doing a statistical investigation. We'll never accept or prove the null hypothesis. All that we are doing is evaluating the strength of the evidence against it. The dolphins getting 10 out of 16 right certainly doesn't prove that they're just guessing. It's just that it's plausible they could have gotten 10 out of the 16 right by purely guessing. Let's recap 3 important vocabulary terms that have come up in these videos that are sometimes confused. It's somewhat unfortunate that the letter P gets used so often. P itself represents the true unknown probability of success occurring, a parameter. In this situation, the long-run proportion of the time that the dolphins would press the correct button. P hat represents the proportion of successes in our sample, in this case 15 out of 16. The p-value represents the probability of observing as many or more successes as we did if the null hypothesis is true. Right now, we perform a simulation to determine the p-value. In certain instances, there are other ways that we can determine a p-value as well. It's also important to note that while in our situation, the p-value represented the probability of observing as many or more successes as we did, there will be other contexts where it might represent observing as many or fewer successes, or simply the number of successes that's as extreme as we did. As we move forward with statistical inference, we'll look at those kinds of situations. A final note about the dolphin study. In order to make general claims about dolphin communication such as this, research needs to be able to be reproducible. And subsequent studies have shown that dolphins are indeed highly intelligent mammals capable of high-level communication. In the slides, there's a link to a National Geographic article describing dolphin communication and research that has been done about it. To recap, in these videos, we've talked about how to state the parameter of interest in a study, state the null and alternative hypotheses using both words and symbols, identify sample statistics, describe how to use simulation to test hypotheses about proportions, determine whether there is evidence to reject a null hypothesis, and explain the meaning of a p-value in context.